It hits you right in the gut, doesn't it? The thought of AI confidently stating something that's just plain wrong, especially when lives are on the line in medicine.
Mm,
You're trying to stay informed, but the sheer volume of information out there can feel like drinking from a fire hose.
it really can.
Today, we're going to cut through the noise and take a focused look at some groundbreaking new research tackling this very issue in medical AI.
Exactly. We're diving deep into a paper that's pushing the boundaries of accuracy in medical visual question answering, or MedVQA.
MedVQA? Okay.
Picture this, an X-ray of a lung with pneumonia. You ask the AI, does this image show an abnormality indicative of pneumonia? And you need a reliable yes.
Right. Not a maybe or something completely off.
Precisely. This technology holds incredible promise for giving both patients and clinicians faster, more accurate insights, but only if we can trust its answers.
And the research we're unpacking, hot off the presses from neurocomputing, received last December and published just this March, is titled MKGF, a multimodal knowledge graph-based RAG framework to enhance LVLMs for medical visual question answering.
It's quite a mouthful.
It is a technical title, yeah, but the core challenge of addresses is something we've all heard whispers about. Large vision language models, or LVLMs, in medicine have a tendency to hallucinate.
That's the term, yeah. Generate incorrect or nonsensical information.
Plus, keeping these massive models up to date with the ever-evolving landscape of medical knowledge is, well, it's a monumental and expensive undertaking.
Hugely expensive. And what makes this paper particularly noteworthy is its innovative approach to this problem. They're proposing MKGF,
MKGF.
a multimodal knowledge graph-based retrieval augment generation framework. Essentially, MKGF leverages a meticulously constructed multimodal medical knowledge graph, or MMKG.
Okay, MMKG, lots of acronyms today.
Ha! Yes, we'll try to keep track. But this MMKG provides LVLMs with the specific relevant medical knowledge they need, precisely when they need it.
So it's like giving it notes just before the test.
Kind of, yeah. The real brilliance here is that it leads to significant gains in accuracy without the need for continuous, large-scale retraining of the AI model.
Ah, so it avoids that huge cost and effort.
Exactly. It's like equipping the AI with a highly targeted and up-to-date reference library for every question it encountered.
And the impact, you mentioned results.
Really significant. The researchers demonstrated around a 10% improvement in accuracy on well-established public datasets like SLAKE and VQA-RAD.
10%, that's quite a jump in this field.
It's a considerable leap forward, yeah. It highlights the power of intelligently providing the right knowledge at the right time.
Okay.
So over our time together, we're going to explore the limitations of previous approaches, then dissect this novel MKGF framework, paying close attention to the design and construction of the MMKG. That's really key.
Right, the knowledge graph itself.
We'll walk through the step-by-step process of how it works, and of course, we'll examine those compelling results and discuss the potential implications for the future of medical AI.
Okay, let's really dig into this. To truly grasp the innovation behind the MKGF framework, it's helpful to understand what came before, right? The paper outlines two primary categories of earlier MedVQA methodologies, discriminative and generative.
That's right. Discriminative methods essentially framed MedVQA as a task of classification.
Classification, okay.
They aim to select the correct answer from a predefined set of possible answers. Think of it like choosing the right diagnosis from a limited list of options.
Like a multiple choice test for the AI.
Exactly. While effective in controlled environments, their fundamental limitation was their inability to handle questions whose answers fell outside that predetermined set. They struggled with the open-ended nature of real-world medical inquiries.
Right, if the answer isn't on the menu, you can't order it. So how did the generative methods attempt to overcome this inherent restriction?
Well, generative methods, fueled by the advancements in large vision language models, sought to address this by actually generating the answer.
Creating it from scratch.
Yes, the core idea was to transfer the broad knowledge and language understanding capabilities of these massive models to the specific domain of medicine. Researchers trained these LVLMs on vast data sets of medical images and their corresponding textual descriptions,
Trying to teach them the links between images and words in medicine.
aiming to teach them the intricate relationships between medical visuals and language. Precisely.
Okay, that sounds like a significant theoretical advancement. What were the practical challenges that arose? I mean, we already mentioned hallucinations.
Right, that was the first major limitation the paper pinpoints. Much like in general-purpose applications, these medical LVLMs exhibited a tendency to hallucinate. When faced with questions requiring specific knowledge they lacked, they would sometimes generate plausible-sounding but factually incorrect answers.
which is dangerous in medicine.
Extremely. The paper illustrates this with an example using LVLM, where it incorrectly identified findings in a pneumonia-related image due to insufficient underlying knowledge about the condition.
So we're back to the initial problem of unreliable AI and the second hurdle.
The second significant challenge was the sheer difficulty and cost associated with updating the medical knowledge embedded within these LVLMs.
Right, keeping them current.
Exactly. These models contain billions of parameters, and the process of fine-tuning them on new medical datasets or knowledge bases to ensure they remain current demands immense computational resources and time. It's a very expensive endeavor.
Okay. This sets the stage perfectly for the introduction of the MKGF idea. How does this framework strategically navigate these persistent challenges?
The central concept underpinning MKGF is knowledge-based retrieval augment generation, or IRAG.
RAG. Heard that term before.
Yes, it's becoming quite prominent. Envision a system that first intelligently retrieves relevant information from an external specialized knowledge repository.
The MMKG in this case.
Precisely. And then utilizes that retrieved information to guide the large vision language model in generating a more accurate and reliable answer. It's akin to providing the LVLM with highly relevant notes or a targeted cheat sheet immediately before it needs to respond to a query.
I like that analogy. It really clarifies the process. So instead of trying to internalize all medical knowledge, it's accessing it on demand, like an open book exam.
Sort of, yeah, that's a good way to think of it. And this RAG-based strategy offers a powerful dual advantage. It significantly mitigates the problem of hallucination by grounding the LVLM's responses in verifiable factual information.
Because it's looking it up.
Right. And it bypasses the computationally intensive and time-consuming requirement of continuously fine-tuning the entire model's parameters.
Okay, that makes a lot of sense. Now, the paper emphasizes that a generic knowledge graph isn't sufficient for this task. What are the unique demands of the medical domain that necessitate a more specialized knowledge source?
That's a critical insight. The researchers highlight a couple of key distinctions. Firstly, in general physical question answering, questions often revolve around a single primary entity, asking about a cat in a photo.
Sure.
However, in RedVTA, a single medical image can necessitate knowledge about multiple interconnected entities. Consider our pneumonia example again. The image doesn't just depict the pneumonia itself, but also the lung.
And maybe other structures.
Exactly. And understanding the intricate relationship between these entities is crucial for accurate interpretation. Secondly, while general images often exhibit clear visual cues, colors, distinct shapes.
A cat looks like a cat.
Right. Medical images, such as X-rays, are typically monochromatic, and the subtle visual distinctions indicative of different conditions or affecting various organs can be far more nuanced and challenging to interpret.
Okay, that makes perfect sense. The complexity and interconnectedness of medical knowledge, coupled with the subtle nature of medical imagery, necessitates a more tailored and detailed knowledge foundation. And this brings us to the MMKG, the multimodal medical knowledge graph. Tell us about the architecture and content of this crucial component. What makes it multimodal?
The MMKG represents a key innovation of this research. At its core, it's a structured medical knowledge graph, meaning it comprises medical entities like organs, diseases, symptoms, and explicitly defines the relationships between them.
Like disease A affects organ B.
Exactly. But its defining characteristic, the multimodal aspect, lies in its integration of not just textual information, but also corresponding images for these entities.
Ah, so text and pictures.
Yes. Therefore, for a specific disease, the MMKG wouldn't just contain a textual definition and associated symptoms, but also representative medical images illustrating that condition.
That incorporation of visual information seems particularly significant, especially given those interpretation challenges in medical imaging you just mentioned. Can you elaborate on the construction process? Building this sounds like a huge job.
It was definitely a substantial undertaking involving a multifaceted approach. They began by leveraging a publicly accessible medical knowledge graph as their foundational structure.
So they didn't start completely from scratch.
No, they built upon existing work. Then, to enrich the textual content, they employed a powerful language model, GPT-4, to generate comprehensive textual descriptions for each entity based on its inherent attributes within that initial knowledge graph.
Using AI to help build the knowledge base for the AI. Interesting.
It is. The prompt provided to GPT-4 essentially instructed it to create concise yet informative summaries for each entity and its associated properties.
Okay, clever. And how did they curate the visual component, the collection of relevant medical images? Where did those come from?
For the image acquisition, they adopted a broad strategy, drawing from three primary sources. A widely used web search engine, Google Images,
Okay.
and 2 publicly available specialized medical image datasets, LACO and PubMed.
Right, established medical sources.
Exactly. This enabled them to amass a substantial collection of visual data covering a wide spectrum of medical entities. In total, they compiled an impressive data set of 20,545 images, representing 409 distinct organ and disease entities.
Wow, over 20,000 images. But as you pointed out earlier, ensuring the quality and relevance of these images is paramount. You can't just pull random stuff from Google Images for medical AI. How did they filter them?
Absolutely critical point. This is where another key part of their methodology comes in. To address the inherent issue of potentially noisy or irrelevant images, they implemented a rigorous filtering process using a pre-trained medical multimodal model known as a MKGF.
Biomed Keep, so a model specialized in medical images and text.
Precisely. It's designed to understand the intricate semantic relationships between medical text and corresponding images. For each entity in their MNKG, they used Biomed Keep to compute a cosine similarity score.
A measure of how related they are.
Yes, comparing the textual description of the entity with each of the collected images. Any image that exhibited a similarity score below a predetermined threshold, specifically 0.28 in this study, was systematically discarded.
So they were essentially ensuring a strong semantic alignment between the image content and the textual description of the medical entity it was supposed to represent. Like, does this image really show pneumonia?
Exactly that. And to further validate the efficacy of this automated filtering process, they also incorporated human expertise.
Ah, bringing in the doctors.
Yes. 3 domain experts meticulously evaluated a randomly selected sample of 1,800 images, categorizing them as either relevant or irrelevant. They even included 200 intentionally noisy images in this sample to test the experts.
See if they could spot the bad ones.
Right. And the experts demonstrated a high degree of agreement in their evaluations, achieving a Fleiss Kappa score of 0.81.
Which is good.
Very good. It signifies substantial inter-rater reliability. This manual validation provided strong confirmation that their automated filtering methodology was indeed effective in maintaining a high standard of image quality within the MMKG.
That level of validation really underscores the rigor in constructing this MMKG. Can you give us a sense of the overall scope and structure? What kind of info does it actually hold?
Certainly, the final MMKG comprises 106 distinct organ entities and 303 different disease entities. Okay. They're interconnected by 2,906 explicit relationships, which fall into 61 unique relation types.
Wow.
On average, each entity has a textual description of about 90 words and is linked to around 50 representative images.
50 images per entity, that's quite a few.
It is. For instance, you might find an entry explicitly stating alveolar proteosis, location lung, clearly illustrating a specific relationship between a disease and the organ it affects. This rich blend of structured text and relevant visuals is what makes the MMKG so valuable.
Okay, so we have this meticulously constructed MMKG in place. Now let's delve into the core of the innovation. How does the MKGF framework actually leverage this knowledge graph to enhance the LVLM's ability to answer medical visual questions accurately? Let's break down those 3 key modules you mentioned earlier, starting with question knowledge similarity computing. What's the goal here?
Right. The primary objective of this first module is to figure out which specific pieces of knowledge within the MMKG are most pertinent to a given medical visual question. This happens during the training phase of the MKGF framework.
Okay, during training. How?
The process starts by using an LVLM, the base model, to generate a detailed rationale for question-answer pairs that are present in the training dataset.
A rationale, like an explanation.
Exactly. It's essentially a textual explanation articulating why a particular answer is correct and relevant for a given question and its associated medical image.
So even during training, the AI is generating explanations for its reasoning. That's a fascinating approach. What happens to these rationales then?
These generated rationales are subsequently fed into a pre-trained text retriever, like BGE, which is good at understanding text meaning.
Okay.
This retriever then calculates a similarity score by comparing these rationales with the textual descriptions of all the individual entities stored within the MMKG. This gives a first-pass indication of which entities might be relevant.
But the paper also introduces an innovative subgraph matching algorithm. What does that add? Sounds more complex.
It is a bit more sophisticated, yes. Recognizing that medical images often involve a constellation of related entities, the subgraph matching algorithm is designed to capture these connections.
Ah, like the pneumonia and the lung connection we talked about.
Precisely. It doesn't solely focus on the similarity between the question's rationale and the description of a single entity in isolation. Instead, it also considers the similarity of its neighboring entities within the knowledge graph.
So looking at the immediate context within the graph.
Exactly. For pneumonia, it also looks at lung. It then integrates the similarity scores of these neighbors, weighted by a predefined hyperparameter alpha. They set it to zero point 0.2 to refine the overall question entity relevance score.
Okay, so it's a more context-aware way of figuring out relevance.
Yes, this approach lets the framework capture more nuanced relationships in the medical domain and identify a more comprehensive and contextually relevant set of potential knowledge.
Okay, that makes a lot of sense. By considering the interconnectedness within the graph, it's more likely to retrieve richer, more applicable information. So having established these similarity scores, what's the next stage? That leads us to the second module, multimodal knowledge retriever training.
Right. In this phase, the goal is to train a dedicated multimodal knowledge retriever using that biomed clip model again that can effectively discern which knowledge, both text and images, within the MMKG is most relevant to a specific medical visual question.
So training a specialist retriever, how?
The training process uses two distinct but complementary loss functions.
Loss functions, measures of error the AI tries to minimize.
Essentially, yes. They guide the learning process. The first is the contrastive loss, LC. This helps the retriever learn to effectively discriminate between images of different entities.
Tell image A from image B.
Exactly. Think of it as training the model to distinguish, say, an X-ray showing a healthy lung versus one showing pneumonia. The paper calls it a K plus one-way classification. K negative samples, different entity images, and one positive sample, same entity image.
So it learns what makes a pneumonia image distinct from a healthy lung image.
Precisely. It maximizes similarity for images of the same entity, minimizes it for different ones.
Okay, that sounds essential for picking the right visual info. What about the second loss function?
The second one is the KL divergence loss, LAL. Its main job is to make sure the similarity predictions made by this multimodal retriever align closely with those question entity similarity scores we calculated in the first module.
The ones using the rationales and subgraph matching.
Exactly. It's basically teaching the retriever to agree with that initial assessment of which entities are most likely relevant. By minimizing the KL divergence, the retriever learns to produce a probability distribution over relevant entities that closely matches the one derived earlier.
Got it. So one loss sharpens visual discrimination, the other aligned it with the text-based relevance assessment. A nice two-pronged approach.
It seems very effective, yes.
Now we arrive at the final module, retrieval augmented generation. This is where the trained system gets to work on new, unseen questions, right? The actual Q&A part.
Precisely. This is the stage where the MKGF framework actively assists the LVLM in answering novel medical visual questions encountered during testing or real-world use.
Okay, how does it work then?
The previously trained multimodal retriever takes the new question and its corresponding medical image as input. It then applies its learned understanding of relevance to search through the MMKG and retrieve the top P most relevant entity textual descriptions.
Top P, like the top few?
Yes, in their experiments, they use the top 3 most relevant descriptions.
So for a new question and image, it fetches the top 3 most relevant text summaries from the MMKG based on both the visual and text cues it learned. What happens with this retrieved knowledge?
This retrieved textual knowledge is then seamlessly integrated as additional context and fed into the LVLM along with the original medical question and the image.
Oh, so the LVLM gets the question, the image, and these relevant snippets from the knowledge graph.
Correct. The LVLM can now leverage this supplementary information from the MMKG to generate a more informed, accurate, and reliable answer. This is the core mechanism by which MKGF effectively mitigates the risk of hallucination by providing pertinent external knowledge right when it's needed.
That's a really elegant way to integrate structured knowledge with the reasoning power of LVLMs. Okay, let's turn to the results. The paper presents some compelling findings. Which data sets did they use to test this?
They conducted comprehensive evaluations on 2 widely recognized and challenging public MedVQA datasets, SLAKE and VQA-RAD.
SLAKE and VQA-RAD. Okay, standard benchmarks.
Yes, SLAKE has diverse radiology images and questions, and VQA-RAD is another established benchmark in this area.
And how did MKGF stack up against other methods?
The results were indeed quite significant. They benchmarked MKGF against a range of existing methods, some non-RAG approaches like MedFlamingo and QMT, and other knowledge-based ARB-RAG frameworks like WikiChat, KAT, Wikilava, VQA, and CRKVQA.
So comparing against the field.
Right. And notably, when we integrated MKGF with both the ALAVaMed 7B model and the state-of-the-art QuattroGPT Vision 7B model, They observed substantial improvements in accuracy.
That 10% figure you mentioned earlier.
Yes, approximately a 10% increase in overall accuracy on both SLAKE and VQA-RAD compared to the baseline performance of those LVLMs used alone without MKGF.
That really highlights the benefit of adding this targeted knowledge.
It does, and importantly, as we discussed, this improvement was achieved without requiring any computationally intensive fine-tuning of the underlying LVLMs themselves.
Right, which is a huge practical advantage.
Absolutely, it underscores the efficiency and cost-effectiveness of the RAG approach here. Furthermore, their analysis revealed that methods which incorporated the visual information from the MMKG as cues during retrieval consistently outperformed those rely only on text.
So using the MMKG's images helped.
Yes. For example, their MKGF approach, combined with Watto-GPT vision, showed over a 5% accuracy improvement compared to Wikilava, which doesn't use visual knowledge graph info during retrieval.
That strongly validates the multimodal aspect, the MM and MMKG.
It really does.
They also mentioned something called Silver Knowledge's results. What was that about?
Ah, yes, the silver knowledge experiments. They were designed to estimate the sort of upper bound performance achievable with this setup.
Like the best possible score?
Kind of. In these experiments, they simulated the question entity similarity step using the rationale associated with the correct answer to guide knowledge retrieval, essentially assuming perfect knowledge identification.
Cheating a little for science?
Ha! Exactly. It bypassed potential errors in the rationale generation and subgraph matching, showing the potential if retrieval was perfect. The fact that MKGF's actual results are still a bit below this silver level suggests there's still room to improve the knowledge retrieval part.
Okay, so MKGF is a big step, but maybe not the final step. Now, to really understand what makes MKGF tick, they did ablation studies, right? Taking parts away to see what happens.
Exactly. Ablation studies are critical for dissecting complex systems. They systematically remove specific parts of MKGF, the contrastive loss, LC, the KL divergence loss, LKL, the subgraph matching algorithm, SBGM, and using visual cues, visual, one by one, and watch the performance.
And what do I find? Did removing these hurt performance?
Yes, significantly. Their findings clearly showed that removing any of these integral components resulted in a discernible drop in overall performance. It really underscores how these parts work together.
Can you give some examples? How much did performance drop?
Sure. Removing the contrastive loss, LC, led to an average performance decrease of over 2%. That shows how important it is for the retriever to visually tell entities apart.
Okay.
Removing the KL divergence loss, LKL, resulted in an even bigger drop, over 5%. That highlights its importance in aligning the retriever's relevance understanding with the initial text-based assessment.
Wow, over 5% just from losing LKL. What about the subgraph matching and the visual cues?
Omitting the subgraph matching algorithm also caused a consistent performance reduction. This reinforces the idea that considering neighboring entities provides valuable context, leading to better training data for the retriever, especially with complex medical images.
This sense.
And furthermore, when they removed the visual cues during retrieval, relying only on text, they also saw a notable decline, again validating the contribution of the multimodal aspect.
So it really seems like each piece, the rationale, the subgraph matching, both loss functions, the visual info, they all genuinely contribute to the overall success. It's a well-designed system where the parts work together.
Exactly. It's not just one trick, it's a synergistic combination of innovations. And the paper goes into even more detail.
Oh, like what?
Well, they analyzed the specific effectiveness of rationale generation and subgraph matching in improving those initial similarity scores. They looked at the impact of retrieving different amounts of knowledge that top p-value, and they tested MKGF's robustness with different LVLMs for different sizes.
Any key insights from that deeper analysis?
One key finding was that both rationale generation and subgraph matching are indeed critical for that initial similarity computation. Performance dropped over 3% when either was omitted. They even showed a case study, a pneumothorax example, where the system failed to retrieve the crucial knowledge without steps.
So those steps are really necessary to find the right starting point in the graph?
Seems so. And regarding the amount of knowledge retrieved at top P setting, performance tended to plateau around retrieving the top 4 most similar entities.
Interesting. So more than the top 4 didn't really help much more.
Apparently not, suggesting a point of diminishing returns.
What about using different underlying AI models? How did MKGF perform then?
They tested MKGF rigorously with both a smaller 7 billion parameter LVLM, LavaMed, and a much larger 34 billion parameter model, Watto-GPT vision.
Okay, small versus large.
And MKGF consistently boosted the performance of both. Perhaps even more strikingly, the smaller LVLM, when augmented with MKGF, actually achieved comparable, sometimes even better performance than the much larger LVLM used alone, without MKGF.
Wow, that's really significant. It means you might not need the biggest, most expensive model if you have this smart knowledge augmentation.
Exactly. It demonstrates the potential of this approach to make high-performing medical AI potentially more accessible, less computationally demanding.
That's a fantastic implication. Did they look at what happens if the knowledge graph itself isn't perfect? Like if it has gaps?
They did touch upon data sparsity. They simulated scenarios where parts of the MMKG entities, relationships, images were randomly removed.
Okay, real world conditions.
Right. Their analysis showed that while performance did gradually decrease as the graph became less complete, which you'd expect, MKGF still provided a significant performance advantage even when the MMKG was only 40% complete.
So it's reasonably robust even with imperfect knowledge.
It shows a degree of robustness, yeah, which is important because real-world knowledge graphs are rarely perfect.
And one last comparison. How did MKGF stack up against just fine-tuning the LVLM, which is another way people try to improve performance?
Good question. It compared MKGF to fine-tuned versions of the Watto GPT Vision-7B model using efficient techniques like LoRa and QLoRa.
Efficient fine-tuning, okay.
Interestingly, their results showed that MKGF, used with the pre-trained non-fine-tuned LVLM, actually outperformed its fine-tuned counterparts by over 1% in overall accuracy.
Really? So MKGF was better than fine-tuning?
In their experiments, yes. It suggests that augmenting with external structured knowledge via MKGF can be more effective and certainly more computationally efficient than even these parameter-efficient fine-tuning methods. They also did some A/B testing with other ERAG methods to further validate that the quality of the images in their MMKG really did help.
Okay, that's a powerful set of results. So to bring our deep dive to a close, what would you say is the most significant overarching takeaway from this research into the MKGF framework?
I think the most significant takeaway is that MKGF presents a really promising and innovative solution to a critical challenge in medical AI that's enhancing the accuracy and reliability of these large vision language models for medical questions without that huge overhead of constant retraining.
Right.
By intelligently leveraging this carefully built multimodal medical knowledge graph, MKGF effectively gives the LVLM the relevant real-world medical knowledge it needs, right when it needs it. And that leads to fewer hallucinations and noticeably better performance.
And what are the key innovative aspects here that really make it stand out? What's the secret sauce?
Well, several things. First, the MMKG itself is a combination of entities, relationships, text descriptions, and importantly, those curated medical images. That's a valuable resource in itself.
Hmm.
Second, that subgraph matching algorithm, that's a novel way to improve knowledge retrieval by looking at the connections between medical concepts.
The neighborhood effect.
Exactly. And finally, the multimodal training strategy for the retriever, using both contrastive and KL divergence losses. That enables it to effectively use both text and images to find the right knowledge. It's really the combination of these pieces working together.
A synergistic effect, as you said. The authors also mentioned limitations in future work, didn't they?
They did, quite rightly. They pointed out that MKGF's performance naturally depends on the quality and completeness of the MMKG itself. Building and maintaining these large, high-quality medical knowledge drafts is still a big challenge.
An ongoing effort.
Yes. And they also acknowledged that MKGF's effectiveness is tied to the capabilities of the base LVLM. As those models get better, they'll likely be able to use the retrieved knowledge even more effectively. So future work could focus on building better MMKGs and finding even smarter ways to integrate that knowledge into the AI's reasoning.
Makes sense. So as we conclude this in-depth exploration, here's a final thought for you, our listener. We've seen how this sophisticated knowledge-augmented AI system can dramatically improve accuracy in the critical domain of medical visual question answering. But this begs the question, what other vital fields could potentially benefit from similar knowledge-driven AI architectures? Could this approach serve as a blueprint for tackling the pervasive issues of hallucinations and other types of AI where, factual accuracy is just paramount?
It's a really interesting question to ponder.
It certainly is. It's a compelling area for future consideration. And for those of you who wish to delve into the technical details further, the researchers have made their source code publicly available on GitHub. You can find the link within the published paper.